Hello, cowboys and cowgirls. This is Dr. Johnson. I am one of the AP Stats teachers at Capella High School, and I want to welcome you to this lesson on sampling distributions. A sampling distribution is different from the things we've talked about before. So far in this course, we've talked about population distributions, and we take samples from the population and we create a sample distribution. And from that sample, we calculate a statistic. In this unit, we're going to talk about in much more detail about statistics. So suppose that you take many samples from the same population, and for each sample, you calculate the statistic. And then you form a distribution of all of those statistics. Well, this unit, we're going to talk about the shape of that distribution of statistics, the spread, and the center. So let's begin. A parameter is a number that describes a characteristic of the population. And for parameters, we always use Greek letters like mu and rho. A parameter is often a fixed number, but in practice, we don't know its value. The best that we can do is take a statistic and make an inference about what that value might be. A statistic is a number that describes a characteristic of a sample, and statistics have notations like x bar and p hat and s. Now the value of a statistic is known as soon as we take that sample, because we can calculate it. But the value of the statistic will vary from sample to sample, and that's something that we call sampling variability. It is important for you to know the notation here, and in this table here, I'm going to talk about the population notation and the sample notation. If it's a mean, the mean for a population is mu, and the mean for a sample is x bar. Now, we're going to use mu and x bar when we're talking about quantitative data. If we're talking about categorical data, then we're going to be analyzing frequencies. And for that, if we're talking about a population, we're going to talk about rho, that is the proportion of the population. And if it's a sample, we're going to talk about p hat. The definition for the standard deviation of a population is the Greek letter sigma. And for the sample statistic, the standard deviation is s, the letter s. For variance, variance of the population, we're going to use sigma squared. And for variance of a sample, we're going to use s squared. So let's do a practice here. A survey was given of 100 Capella High School students. 4% of the people in the sample reported that they can juggle. What is the population, the sample, the population parameter, and the sample statistic? So here we are. The population is all CHS students. The sample is the 100 CHS students who were sampled, 100 from whom we gather data. The population parameter is rho, the proportion of all CHS students who can juggle, and the sample statistic is p hat, the proportion, that is 4% of the sample who can juggle. Now, there are different types of distributions, and we've talked about the first two already. Population distribution, that shows every individual in the population. A sample distribution, that shows every person in the sample. And what is the new thing that we're introducing here is the sampling distribution. So just as a review, population distribution is a frequency distribution of the entire population, and it can have many different shapes. A sample distribution is a frequency distribution of a sample, and it too can have many different shapes. Now, you shouldn't be surprised to know that the sample distribution and the population distribution often have pretty much the same shape. But now we have this new thing right here, a sampling distribution. A sampling distribution of a statistic, x bar or p hat, for example, is a distribution of values taken by that statistic in all possible samples of the same size from the same population. So if we take many samples, well, let's say if we take all samples of the same size, and for each sample we calculate a statistic, then the distribution of those statistics is itself a sampling distribution. So now we have some new notation for sampling distribution, and the notation is in the column on the right. This is the new notation that you need to know for sampling distribution. The average of all my x bars is represented by this symbol right here, mu with a subscript x bar. The average of all my p hats is represented by this symbol right here, mu with a subscript of p hats. The standard deviation of all my x bars is represented by this symbol, and the standard deviation of all my p hats is represented by this symbol right here. Now, I've given you two new formulas. The formulas are on the bottom. There's the formula for the standard deviation of p hat and the formula for the standard deviation of x bars. This graph illustrates what we're trying to do here. So let's look at the graphs on the left first. Let's say we have the population and we take every single sample of the same size from that population, and for each sample I'm going to calculate a p hat. Then my distribution of all of those p hats is a sampling distribution. On the right side we do the same thing for mean. So suppose the red graph is the distribution of the population, and I'm going to take every possible sample of the same size, and for each of those samples I'm going to calculate an x bar. Then I want to calculate the average of all of my x bars. That's the symbol mu with the subscript x bar. Now, what are we looking for in good estimators? Estimators are examples of estimators are p hat and x bar. What do we want to see in good estimators? Well, the first thing we want is we want our estimators like x bar and p hat to be unbiased. So one of the properties is lack of bias. A statistic used to estimate a parameter is an unbiased estimator if, on average, the value of the estimator is equal to the population parameter. In symbolic notation, I write the expected value of the statistic is equal to the population parameter. If that's true, then the statistic is said to be unbiased. Another way of saying it is that an estimate is unbiased if it is centered on the parameter value. Okay? Bias means that the results are not accurate or not correct. So if you are asked to describe a bias, you want to say that the results are not accurate or not correct. The amount of bias is equal to the difference between the expected value of the statistic and the parameter. An unbiased estimator does not mean that it's a perfect estimator. An unbiased estimator will almost always provide an estimate that is not equal to the value of the population parameter. It is all called unbiased because the center of the statistics sampling distribution will be centered on the parameter value. To reduce bias in a sample, use random sampling. That's the remedy. To reduce bias in a sample, use random sampling. Increasing the sample size will not reduce bias. Another thing that we're looking for in good estimators, low variability. The variability of the statistic is described by the spread of its sampling distribution. High variability means that the results are not precise or not exact. To reduce the variability, use a larger sample. That's how you get a smaller variability of your sampling distribution. Use larger samples. The spread of a sampling distribution does not depend on the size of the population, as long as the population is at least 10 times as large as the sample. The size of the variability of a statistic depends on the sample size, but it does not depend on the population size. Now here's a graph showing, illustrating the meaning of bias and variability. On the upper left, we have low variability and low bias. That's what we like. You can see that my statistic, the distribution of my statistic is centered over the true value, and all of my statistics are tightly clustered together. That's what we like to see. On the upper right, again, I have low variability. All of my statistics are clustered close together, but this time I have high bias. They are not centered over the true value. In the bottom left, I have high variability. Notice how spread out my statistics are. But I have low bias. They are, in fact, centered over the true value. And on the bottom right, I have high variability and high bias. My statistics are spread out, and they're not centered over the true value. Okay, here's another slide illustrating precision and accuracy. I'm not going to discuss it. You can pause your video here and take a look at it. But I do want to take a little bit of time and explain this spreadsheet right here. I calculated I created a sampling distribution of different statistics from a very small population. My population is these numbers right up here in the upper left-hand corner. It consists of the numbers 1, 2, and 12. It is certainly not a symmetric distribution, but it consists of only those 3 numbers. So over here on the left-hand side, I created all possible samples of size 2 from those 3 numbers. There's 9 of them right there. And for each of my samples, I calculated the mean, the sample median, the sample variance, the sample standard deviation, and a few other statistics. Then I took, for example, here in this column, I have my sample means. Here's my sample means. And I calculated the average of my sample means. And notice that, in fact, the average of my sample means is equal to the population parameter. So we can say that the sample mean is an unbiased estimator of the population mean. That's a good thing. That's what we like to see. So now I'm going to move over here to this column on sample variance. Sample variance. Again, for each of my samples, each of my 9 samples, I calculated the sample variance using this formula with the n-1 in the denominator. And then I calculated the average of all of my sample variances. And what do you know? The average of my sample variances is equal to the population variance. Up here I calculated the population variance to be 24.67, and that's exactly the average of my sample variances. So sample variance is considered an unbiased estimator of population variance. But remember, with in the formula for sample variance, we had an n-1 in the denominator. And that's important. The reason why we calculate sample variance with n-1 in the denominator is so that sample variance is an unbiased estimator of population variance. That explains why we have an n-1 in the denominator of the formula for sample variance. Now, let's take a look at sample standard deviation. Here in this column, I calculated the sample standard deviation for each of my 9 samples. And then I calculated the mean, and what do you see here? You see that the average of my sample standard deviations is not equal to the population standard deviation. So sample standard deviation is a biased estimator of population standard deviation. That's all I have to say. You can look at this slide in more detail, and I'll make this slide available on Schoology. So that's it for today. Thank you very much.